Hello, this is Mr. Smith with reading quiz number 6, all about rates of change. We will be studying average rates of change and instantaneous rates of change as we go along, and they will form the foundation for the rest of our calculus experience. So let's take a look. Some definitions. First, we will call our definitions for average rate of change, which we studied in our lab. Average rate of change is just like slope between 2 points, x equals a and x is equal to b. And as the formula is f of b minus f of a over b minus a. The instantaneous rate of change is what happens as the point b approaches the point a. And so when we consider that, we consider the idea of the limit. The instantaneous rate of change is the limit as b gets close to a, or approaches a, of f of b minus f of a over the quantity b minus a. I like to think of average rate of change if you're traveling in a car and you travel for 300 miles over the course of 6 hours, then your average rate of change is 50 miles per hour. But your instantaneous rate of change has more to do with the speed that you would see on your speedometer. It's your instant velocity. And so you might not be going 50 miles per hour the whole time, but over the course of time, then your average velocity would be 50 miles per hour. Two other terms, a secant line is a line passing through 2 points on a curve, and the slope of the secant line is our average rate of change, or AROC. The tangent line is a line passing through a point on a curve with the same slope as the curve at that point. The slope of the tangent line is IROC, or instantaneous rate of change. The key thing to remember about a tangent line is that the tangent line shares both the slope and a point of a particular curve at a particular point. So we now introduce the term derivative, which is oftentimes used to describe a function of our instantaneous rate of change for another function. So we use this in a couple of different contexts. The derivative at x is equal to a means the instantaneous rate of change of f at x is equal to a. Derivative means the new function that describes the IROC at any values as long as that IROC exists. And because of the nature of the concept, this was a subject that was explored in many different areas, and so because of the different people who have helped explore the idea of the derivative, we have many different notations. Let's give you a little bit of a preview of that. We'll see f prime of x, which is the Lagrange notation. We also might see y prime. That's the notation that we'll probably be seeing the most since we use function notation the most. The Leibniz notation, we've got dy dx. As long as y is a function of x, we consider this another popular sort of notation. Newton's notation uses the dots. We oftentimes see this in other scientific fields, but very rarely do we see it in calculus. So y dot would represent the derivative of y. The way we pronounce this is we say if x is the independent variable and y is the dependent variable, we are taking the derivative of y, of that function, with respect to x. So key the words being there with respect to. If we had dl dt, then we would say that the derivative of L with respect to t. If our function was g of m, g prime of m, which is how we would pronounce the Lagrange notation, would be the derivative of g with respect to m. So remember, derivative of the dependent variable with respect to the independent variable. We also say that we can have a left side derivative and a right side derivative, or a derivative from the left and a derivative from the right. And just like with limits, we put a little negative or a little positive sign to indicate that that's what we're doing. Finally, we have a term called differentiable. We say a function is differentiable at a point if the limit of the difference quotient exists. Well, the difference quotient has to do with our instantaneous rate of change. And if our instantaneous rate of change's limit exists, then the function has a derivative at that point. And we use the term differentiable to describe that. So, a couple of examples from the reading. Example number 2. Consider the function y is equal to x squared plus 1. The first part asks us to find the average rate of change of y with respect to x over the interval 3 to 4.5. So, just like we would with slope, we plug in our x value, 4.5. We plug in our other x value of x equal to 3 into our function, and we find our function values. Change in the function over change in x, just like we do with slope. When we work that out, we get an average rate of change of 7.5 over that interval. Use one of the methods from example 1 to approximate the instantaneous rate of change at x is equal to 4. Well, we've got 3 different techniques that we can use to approximate instantaneous rate of change. We can take the point itself and a point just to the left of it. We can take the point itself and a point to the right, which we call the right method. Or we can take 2 points close to the point itself, but on either side, on left and right, which we call the straddle method. And that's what we do right here. We take the point x is equal to 4.01 and x is equal to 3.99. We plug those into our function, we subtract, and we find that the instantaneous rate of change at x is equal to 4 is 8, which is technically an approximation here, but in fact is the actual value when we work it out. Use the limit definition to find the instantaneous rate of change of f of x equals x squared plus 1 at x is equal to 4. So remember, our instantaneous rate of change is a limit of our average rate of change. Right? So in this case, we know that one of our points will be x is equal to 4. And we want to see what happens when we take our x's and get them closer to 4. So we write our average rate of change between the point x and between the point x and the point 4. And when we do it, we get limit as x goes to 4 of x squared plus 1 minus 17. And that's the 17 comes from plugging 4 into our original function. And we divide by our x minus 4, which is our change in x. The great thing about this is we have a simplification on the top to the limit as x goes to 4 of x squared minus 6 over x minus 4. All of those wonderful limit problems we've been practicing with, we can see that we can factor our numerator and cancel out the x minus 4 factor, leaving just x plus 4. Limit as x goes to 4 of x plus 4 is just 8. Hey, that matches up with what we got in the previous part. Maybe there's a connection. Find the instantaneous rate of change of y with respect to x for any general point x sub 0. So rather than x is equal to 4, we'll just call it x sub 0. So substituting x sub 0 in for 4, we get x squared plus 1 minus x sub 0 squared plus 1, making sure that we keep parentheses in our subtraction, divided by x minus x sub 0. Right, so we substituted x sub 0 for 4. We can cancel, so we end up with x squared minus x sub 0 squared over x minus x sub 0. We can factor the top and cancel, so we're just left with a factor of x plus x sub 0. Plugging in x sub 0 just like we did with the 4 up here, we get 2 times x sub 0. That makes sense because now when we plug in x is equal to 4, we get the derivative or our instantaneous rate of change to be 8. 2 times 4 is 8. Example 3 from the reading. The graph below, down here in the light blue, represents a position curve for the height of a ball over time. The height is measured in feet and the time is measured in seconds. Answer the following questions regarding the curve. When is the instantaneous velocity equal to 0? So our velocity, when we're dealing with objects in motion, is our derivative. And so just like we talked about on previous reading quizzes and in labs, the derivative represents the slope of our function. Our instantaneous velocity is 0 when the slope of our position function is 0. And this happens at t is equal to 1 at our peak. We would be able to draw a horizontal line at that point, which would match the slope of the function at that point. Approximate the average velocity on the time interval 0 to 1. Or actually, what is the average velocity? At f of 1, our position function is at 16. At 0, our position function is at 0. So we do an average rate of change on that since velocity represents our derivative. And we get 16 meters per second. Excuse me, that should be feet per second. I hope you caught that. When is the speed a maximum? And that question is asking us, when is our slope the steepest, either positive or negative? And if we're trying to estimate what our slope looks like, it appears that our slope is the most positive or negative at 0 and at 2. And in fact, we will distinguish later on between speed and velocity. And in our case, when our velocity is negative, in other words, when we have a negative slope, we still have a very, very fast moving ball. So, next part. Come up with a tangent line equation to the graph at x is equal to 2. In order to do this, we need an instantaneous rate of change. So one approximation would be trying to find out what the height of the ball is at time 1.5. And at time 1.5, our height is 12, approximately. All right, so we use that along with our f of 2 value, which is 0. We get an instantaneous rate of change approximating it with an average rate of change. When we work it out, we get negative 20 meters per second. Thus, our tangent line would be y minus 0. That should be a minus 20 times t minus 2, or y is equal to negative 20 times, or negative 20t plus 40. Sorry for the typos. Section 3, tangent line basics. As we mentioned before, tangent line is created by using two pieces of information, the value of a function at a point and the slope of the function at that same point. Tangent lines allow us to approximate the value at a certain point, but the accuracy only lasts really close by that x value that we're dealing with. So here's a worked problem. Given that f of x equals x to the 7th minus 13x plus 10, find a tangent line at x is equal to 1, and then use that tangent line to approximate f of 0.98. I have a demonstration right here, a little graph off to the side. In red is the function x to the 7th minus 13x plus 10, and blue will be our tangent line. So we need a point at x is equal to 1 and a slope at x is equal to 1. We notice that f of 1 is equal to negative 2 when we plug in. We can also find that the derivative, using a secret rule that we haven't really talked about, the derivative is 7x to the 6th minus 13. You probably know what that is. F prime of 1 is therefore equal to negative 6. So using our point slope form, we get y plus 2 is equal to negative 6 times x minus 1, which reduces to negative 6x plus 4 equals y. So this, by the way, right here, in case you didn't pick up on this, is the power rule, which we have mentioned briefly in class. It's easiest to make an approximation when we're in point slope form. You must use an approximation sign since we are, after all, approximating. So this last part, we want to find f of 0.98. We plug in 0.98 in for our x. We work it out, and we get negative 1.88 when we plug the x value into our tangent line. Notice that the actual value, if you were to plug it into the function, is negative 1.872. So our approximation is pretty close. Last guided practice here. Suppose we had a table which describes f of x, which is a differentiable function. Selected values are given in the table below. Part A asks us to find the average rate of change in the interval 2.560 to 3.5. Just like with the previous average rate of change problems, we cite our table. We make sure that we start with our formula, f of 3.5 minus f of 2.56, divided by 3.5 minus 2.56. I'm big on making sure that you indicate that you've used your table. We plug in our values. We solve, we get negative 0.957. Part B, use the chart to approximate the instantaneous rate of change at x is equal to 3. So we're going to approximate with the only values that are close to 3, which really close to 3, which are 2.98 and 3.004. When we plug in to our formula, we evaluate it, we get approximately negative 1. So it's important, and here we use the straddle method because those are the only values that were extremely close to 3, and we actually didn't have a value at 3. Find an equation for a secant line for f of x that goes through 2.56 and 3.5. For a secant line, we need to find the slope and we need to find a point. The slope of a secant line is our average rate of change. Because we're dealing with 2 points, we're basically finding the slope between the 2 points. In part A, we already found out that the AROC was 0.957. We could use either point. In this case, we use 2.560 and 0.549. So thus the secant line is y minus 0.549 is equal to negative 0.957 times x minus 2.56. And note we can leave this line in this form and we don't worry about simplifying. You don't want to have any algebra errors that cause problems. Find a line tangent to f of x at 3, 0.141. So again, in part B, we approximated our slope. For our tangent line is our IROC, which is negative 1. We plug that in along with our point and we get y minus 0.141 is equal to negative 1 times x minus 3.